Far yesterday as I had planned, so I'm going to pick up where I left off. And hopefully this morning what I'll be able to get through is finish talking about the quantum Hall effect and the Chern number, do that kind of fast, and then talk about topological insulators. Okay, so the main lessons from last time were first the idea of topological states that that are characterized by maybe some topological invariant, and you can't get from one to the other without crossing a gap, or without the gap closing. And then we did this example in one dimension where we recognized that the electric polarization in one dimension is closely related to the Berry phase of the occupied block states. And we wrote down this model, the Sushri-Verheeger model, which provided we imposed some extra symmetries, either the chiral symmetry or the reflection symmetry, had distinct topological phases, okay, which we could sort of understand. But if we didn't have any extra symmetry, then every one-dimensional insulator is the same as every other one-dimensional insulator. There are no topological classes. Okay, so there's a sense in which in one dimension there's no topological, there's nothing topological if you don't have any symmetries. But what I want to do first is I want to tell you about a one-dimensional situation where there is topology, and this is an important example which I think we can understand, and this is the thallus charge pump. So if I have a one-dimensional insulator, then what I can imagine doing is I can imagine considering an adiabatic cycle where I change the Hamiltonian in time through some periodic orbit. Okay, and so I want to imagine a Hamiltonian now, which is a function of k, but it's also a function of another parameter, which I can call time, and it's periodic. And so the simple picture that I want you to have in your head is just the nearly free electron gas, where I have electrons which are locked in a periodic potential. Okay, and then as a function of time, I can just slide that periodic potential over by one space. Okay, and in doing so, it's obvious that what I do is I pump an electron from one end to the other. Okay, and so I'd like to think about how we can characterize that. And so clearly, what has changed in going from the start to the finish is you've changed the electric polarization. Now the Hamiltonian has come back to where it started. Okay, so the Hamiltonian is the same at the beginning and at the end, but the polarization has changed. And so, like I said, we can characterize the polarization by the Berry phase. Okay, and so I can compute the change in the polarization as the difference between the Berry phase at the beginning and the Berry phase at the end of the cycle. Okay, now the thing we know is that the Hamiltonian at the beginning and at the end is the same. So there's a sense in which the Berry phases have to be the same, except the Berry phase is only defined modulo an integer. It has this intrinsic ambiguity. Okay, and so the interesting thing then is if this change then can be an integer. And so now, of course, we can write the change in the Berry phase as we can use Stokes' theorem to write that as the integral over the entire two-dimensional plane here, okay, of the curl of the Berry connection. So this is manifestly gauge invariant, and the thing is, though, is that it's guaranteed that it has to be an integer. Okay, so this integral of the flux over the entire surface, where now since this line and this line are really the same, I can think of this entire space as being now like the surface of a donut. Okay, it's like a torus. Okay, and so the integral of this Berry curvature over the entire torus is guaranteed to be an integer. Okay, and this integer is the Chern number. Okay, and again, it's very instructive to think about this in the context of this simple model, this two-level Hamiltonian, where, again, I can think of the Hamiltonian as being described by a vector D dotted into a Pauli matrix. And so now this vector D is going to be a function of both K and T. And I told you that the Berry phase you can think of as just the solid angle. The Berry phase on any loop is just the solid angle swept out by D. And so what that means is that what this Chern number is it is just adding up the total, it's counting the number of times this D vector wraps around the sphere. Okay, and so that's a sort of a simple picture of this topological invariant. It's just a winding number, winding number for the the map from the torus onto the sphere. It's the number of times it wraps around. Okay, and it's obvious that has to be an integer. Okay, so this is a simple way of thinking about the Chern number, and so this this understanding of the Chern number can be now applied to understand the integer quantum Hall effect. And to do that, the connection between this picture and the integer quantum Hall effect is a sort of a beautiful argument. Yeah, question. Is there a metallic state? No, there's a gap the whole time. So you're saying as I'm advancing T, then no, the gap stays open the whole time. Okay? Because So what this Chern number is characterizing, it's not characterizing the Hamiltonian at any particular time. It is characterizing the family of Hamiltonians parameterized by T. And for every value of K and T, there's a gap. Okay.
Sorry, this is a torus in KT plane.
Huh?
This is a torus in KT plane.
Yes, that's right.
I think the arrows should be in the same direction because you identified,
No, they're not in the same direction because I'm taking the difference of the polarization afterwards and before. Okay, and so this would be 0 if it were not. So okay, this is an important thing. If my wave function U was defined continuously over the entire torus, then obviously this line and this line are the same line, so these two would be equal to each other. Okay, I just be, this one would just cancel out this one, and so this n would be equal to 0. So what this tells you is that having a non-zero value of n is an obstruction to defining the wave function continuously throughout the entire parameter space. Okay, and so that's sort of a important a consequence of having a non-zero Chern number. It's an obstruction to choosing this continuously everywhere. Okay. Yes.
How would the picture change if you had defects in the one-dimensional crystal?
Defects?
Yeah.
What kind of defects?
Well, either way.
Do I have a gap? So if I continue to have a gap, then I think the picture doesn't change. Yeah. Yes.
If I took two families of Hamiltonians, one where I shift 1 unit of charge to the right in this period, one where I shift 2 units of charge to the right in this period, and I try to, say, adiabatically connect the two, or find a family of transformations from one to the other, do I have to pass through a gapless state?
Yeah, I think so. I mean, so you can't change 1 to 2 continuously.
Yeah.
Yeah. Yeah. All right. Okay. Okay. So for the quantum Hall effect, there's this very deep and beautiful argument, which is nice and simple, which originally was due to Bob Laughlin. And so the idea is the following. So let's imagine that I have a gapped system, a two-dimensional system that is gapped. Okay, and I have in mind thinking of it as the quantum Hall state. Okay, and so what I'm going to do is I'm going to imagine putting this system with periodic boundary conditions going around in one direction. So it's like I'm wrapping it onto a cylinder. Okay, and so then what I'm free to do is I am free to apply magnetic flux down the whole of the cylinder. Okay, and so what Laughlin considered doing was what happens if you adiabatically turn the flux up from 0 to the quantum of magnetic flux h over E. Okay. Now, the thing that's special about the magnetic flux quantum h over E. Now, of course, the magnetic field is not anywhere where the electrons are. So the electrons don't see the magnetic field. They only couple to the vector potential of the that's on the cylinder. And so what that means is that when the flux is h over E, you can do a gauge transformation where you just change the phase of the electrons in a way that advances by 2 pi, do a large gauge transformation, which eliminates this h over E flux. So the process of adiabatically advancing the flux by h over E is just like a thallus pump. Okay, so you've come back to where you started. Okay, and so the question then is, so viewing this cylinder as a one-dimensional system, then you could imagine that a charge could be transferred from one end to the other. And now that is exactly what happens in the integer quantum Hall effect. Because in the integer quantum Hall effect, you have a Hall conductivity. And so let's think about what happens when you turn up the magnetic flux. So when you're changing the magnetic flux, then Faraday's law tells you that you have an electric field that goes around. Okay, so you know the curl of the curl of the electric field is minus dB dt, right? And so that tells you have an electric field going around the cylinder, and since you have a Hall conductivity, that means that there is a current proportional to that electric field and sigma xy. Okay, and so in the process of turning the flux up from 0 to h over E, then there is a net flow of charge from this end to this end, and you can calculate it just by integrating the current over time, and what you learn by doing that is that you just get sigma xy times h over E. Okay? Yes?
I never really understood how this is connected to the quantum Hall effect, because there you have the magnetic field that's going through the sample.
I'm not talking about that magnetic field. I'm talking about, yeah, so then there would be, so that magnetic field would be coming out. But I don't necessarily have to have a uniform magnetic field coming out. I just want to imagine that I have a two-dimensional state, which it could be in a uniform perpendicular magnetic field, but we'll see that you don't have to have a uniform perpendicular two-dimensional magnetic field. All you need is you have to have a broken time reversal symmetry. It has to know whether it's plus or minus, but you don't need to have a uniform perpendicular magnetic field in order to have a quantum Hall state. Yeah. So the point is, this magnetic flux, the flux that I'm talking about, is not that magnetic field. It's a magnetic field which, where the magnetic field never, crosses the electrons. Okay. All right. Good. Okay. So what this tells us is that given a sigma xy, the change in the charge that gets pumped, or the change in the polarization of this one-dimensional system, has got to be sigma xy times h over E. And so what we know is that since we're coming back to where we started, the only thing you could do is transfer an integer number of electrons. Okay, and so that tells you immediately that sigma xy has to be an integer multiple of E squared over h, and in fact, this integer n is the Chern number characterizing this one-dimensional thallus pump, which is parameterized by the magnetic flux. Okay, so this is a way we can sort of understand the Chern number characterizing the two-dimensional quantum Hall effect in terms of the Chern number characterizing this one-dimensional thallus pump. Okay, now what is useful to do, so in order to make this be sort of more clearly related to the band structure of the two-dimensional insulator, what is useful to do is to consider this cylinder to be just one unit cell wide. Okay, so I can imagine it's made out of, you know, my crystal, and so what I'm going to do is I'm going to choose one of the directions of the crystal and have periodic boundary conditions just over one unit cell. Okay, and so yeah.
Where is the state is actually a fractional quantum Hall state?
Ah, yes. That's a very good question. So of course, in the fractional quantum Hall state, you know that you can have a Hall conductivity which is, say, 1/3 of E squared over H. Okay? And that contradicts the theorem that I just proved to you that says that the Hall conductivity can only be integer multiples of E squared over H. Okay, so that's a puzzle. So there must be some assumption that I am making here which is violated in the integer quantum Hall effect. And the assumption that, that I am making is that the ground state is unique. Okay, so which in fact, so in a band theory, of course, it is, because the ground state is just filling the valence band, and the ground state is unique. Okay, so what in fact occurs in the fractional quantum Hall state is if you put the fractional quantum Hall state on a torus with periodic boundary conditions, the ground state has a topological degeneracy. Okay, and that's where that argument breaks down. Yes.
So about integer quantum Hall effect, it's also usually mentioned that we need to have sufficient disorder in the system. Can you elaborate on it?
Well, so no. I mean, so this is in a so usually you need to have sufficient disorder so that your states are localized. Okay, but if you have an energy gap, okay, then the states inside the energy gap are automatically localized. You know, if you try to have a state inside the gap, then it's going to be decaying exponentially. Okay, and so in this sort of band structure integer quantum Hall effect, which I'm going to be describing, then disorder is not essential. Yeah.
But even for the fractional quantum Hall, if the system is finite, then technically speaking, it's still unique. I mean, the ground state is still unique. So what breaks down for a finite system?
Well, then you don't have a precisely quantized Hall conductivity. Yeah.
Could you say where we use the uniqueness of the ground state?
What's that?
When do we use the uniqueness of the ground state?
Well, it's when I talked about the adiabatic, so when I'm talking about adiabatically threading the magnetic flux, I'm declaring that as I adiabatically tune my system, I'm staying in the same state. Okay, and that's reasonable if the state that I'm in is separated by all of the other states by an energy gap that is much bigger than 1 over the time that I'm doing my adiabatic transformation in. So if I have degenerate states, that argument breaks down. And so in fact, when I thread the flux, then I'm coming back to a different state. So when I thread H over E flux, the state that I am in is not the same state that I started in. Okay.
But I'm not really sure what's wrong with that. You can still define like these collection of subspaces as you vary the parameter, and the subspaces themselves close on themselves. If it's
no, but in order to get back to the same state in the fractional quantum Hall state, nu equals 1/3 fractional quantum Hall state, you have to advance the flux by 3 finite. Okay. Yeah. All right. Okay. So this gives us a way of thinking about the Chern number. Now, so if I think of this cylinder as just being a single unit cell, Okay, then so let's think about what block states are like. So when you have the crystal momentum, what that is telling you is that the wave function sort of advances by e to the I k dot the lattice constant when I go by one lattice constant. Okay, and so this magnetic flux is playing precisely the role of the y component of the crystal momentum. Okay, and so so what that means is that I can think of the band structure now of my two-dimensional insulator, which is now a function of kx and ky, and I can compare the polarization, if you will, which is the Berry phase over two different values of ky, which are related by 2 pi over a. Okay, and so this is the same picture that I drew before, where now I'm drawing it as a two-dimensional Brillouin zone, which is a torus. Okay, and so again, the Chern number is going to be the integral of this Berry curvature over the two-dimensional Brillouin zone. Okay, and so this hopefully gives you some understanding of why the Hall conductivity is a Chern number, okay, and how it's related to the via this Laughlin argument to the Chern number that characterizes a one-dimensional thallus pump. Okay. Now, there's another calculation you can do, and this is a calculation which takes a little bit of algebra, so I didn't want to sort of take you through it. But sigma xy, the Hall conductivity, is something that you can compute in a system using linear response theory. Okay, and so that's a standard sort of tool that we have to calculate things. Linear response theory. You calculate a current correlation function to calculate the sigma xy, and that in fact is what Thallus did. What he recognized is that when you calculate sigma xy, what you get is precisely the formula for the Chern number. Okay, so this argument is sort of another way of understanding that. Yeah.
But without that argument, how do you know that this is actually the conductivity? Because we initially started out with something.
Well, no. So the argument is this. Okay. So when I thread the flux, the amount of charge that gets pumped is proportional to the Hall conductivity.
What are you doing with the sample when you what are you varying as you look at the sample? How are you measuring this?
So what I'm doing is now I'm not telling you how an experimentalist would do this, okay? But in principle, what I'm doing is I have a little solenoid that's going down the middle of this cylinder, which controls the magnetic field, and I'm turning the current in that solenoid up so that the magnetic flux grows, and I am measuring how much charge there is at the end of this cylinder.
Are you saying that's a physical cylinder? Like I'm
Yes.
going to construct this in my lab?
You don't have a lab. So it's physical to the extent that one can contemplate physically doing this. Okay, so an experimentalist would have a better way of doing this. All right, but yes, I'm saying if you could arrange this quantum Hall state on a cylinder and actually thread the magnetic flux, then actually the charge at the end would change. Okay. All right.
In this picture, the next slide. Yeah, in this picture, the two arrows are in the same direction.
I'm sorry, I should have drawn them. That was a mistake. Okay. So this one was wrong, the other one was right. Yeah. Okay, sorry.
This one is right, the other one is
No, this one is wrong. Sorry about that. Yeah.
So the linear response calculation gives you this integer. It's still like a linear response calculation. So how do you, whereas the Laughlin argument seems to not depend. I mean, the linear response calculation, you can imagine there being corrections of higher order.
Yeah, but again, it's in the adiabatic. So in the adiabatic limit, then this electric field is very, very small. right? Because I'm doing it very, very slowly. So the linear response, the linear response is going to be the only response that matters. Yeah. Okay. All right.
Sorry.
Yes.
Thank you for your patience. Just real quick. If the state on the cylinder is a Hall state, why don't you need that radiomagnetic field? Did you say you didn't need it?
Well, so what I'm saying is that I don't need to have a uniform radial magnetic field. So wait till the next slide. I'm going to show you how you can have an integer quantum Hall state without a uniform radial magnetic field. Now, the first way we're used to thinking about the integer quantum Hall state is to have a filled Landau level. Okay? And so obviously, in order to have a filled Landau level, in order to have a Landau level, you need to have a uniform, a perpendicular magnetic field. Okay? I'm going to show you another way to do it. Okay? And this is Duncan Haldane's way of doing it. Okay. All right. Okay. So this leads me to let me digress for a minute about graphene, because this is a wonderful model system where you can see a lot of this physics at work. Okay, and so graphene, of course, is and this is going to be sort of it's like the two-dimensional version of the Sushri-Verheeger model. It's the simplest model that you can write down. It's a model that has a unit cell that has two atoms in it. So your block Hamiltonian is just going to be a 2x2 matrix again. Okay, so basically, it's just like the Sushri-Verheeger model. I have sites on a honeycomb lattice, and I have hopping between the nearest neighbors. Okay, and so my Hamiltonian again is going to be my block Hamiltonian is going to be a 2x2 matrix. Okay, and then the eigenvalues of that block Hamiltonian are just going to be the magnitude, plus or minus the magnitude of that 2x2 matrix. And given the three bonds that you have, you can write down what this D vector will be. Okay, so that's not too hard to do. Now, one thing that's clear, since again it's a bipartite lattice and I only have A to B hopping, okay, then it has the same kind of chiral symmetry that the Sushri-Verheeger model had, which means that the D vector lives in the XY plane. Okay, so now the D vector is a function of a two-dimensional momentum, and so one of the things that can happen if you have a two-dimensional unit vector, it's sort of like an XY model. Okay, so in two dimensions, what you can have is you can have point-like defects where the around which this D vector wraps by 2 pi. So it's sort of like a vortex in the XY model. So those are things which would be sort of topologically stable. Okay, and in fact, that is what happens at the corners of the Brillouin zone. So at the corners of the Brillouin zone, there are these singularities around which the D vector wraps by 2 pi, and there you know that at the singularity, the magnitude of the D vector has to go to 0. Okay, because otherwise you couldn't, you wouldn't be able to have this non-trivial winding. Okay, and then when the magnitude goes to 0, then you have this gapless point, this gapless Dirac point. Okay, and near this gapless Dirac point, we can expand and we can write the Hamiltonian as basically Q dotted into sigma x and sigma y. Okay, all right. Okay, so this is the simple picture of graphene. Now, of course, just like in the Sushri-Verheeger case, the gaplessness of this is going to be protected by some symmetries, and it's very useful to think about the symmetries that are protecting this Dirac point. And or another way of saying it, you can ask the question: let's suppose I wanted to get rid of the energy gap in graphene. How might I do it? Okay, so there are two ways you can do it, which are interesting. So one way you can do it is you can make the two atoms different. Okay, so I can, for instance, you might think instead of having graphene, you could have boron nitride. Yeah.
So this whole electron hole symmetry, the symmetry now, the particle
It's as artificial a symmetry as it was for polyacetylene. Okay, so real graphene does not have this particle hole symmetry. Okay, but the simple model that I'm writing down does, and for our purposes, it's okay. It doesn't, that doesn't, it's all right.
So you're neglecting spin?
At this point, I'm neglecting spin. I will remember spin in a few minutes. Yeah. Okay. All right. Good. So if you break the symmetry by making the two atoms different, then one thing you can see is so the original graphene lattice has a inversion symmetry about the say center of a hexagon. Okay, so that has an inversion symmetry, but if I make the two atoms on the A and B sublattices different, then that inversion symmetry is violated. Okay, and so what the effect of that is to introduce a mass term into the Dirac point, where you see, so by breaking the inversion symmetry, then the D vector no longer has to be in the xy plane. Okay, and so that means that at the Dirac point, where sort of the x and y, so at the Dirac point, it's just going to be pointing in the z direction. Okay, and so the interesting question is, so we have these two Dirac points, one at k and one at minus k, basically. Okay, and so the interesting question is whether the d vectors are pointing in the same direction or opposite directions. Okay, if they're pointing in the same direction, that's what, if you have inversion symmetry, then at k and minus k it has to be the same. Okay, and so that means that at both k and minus k, then the d vector sort of visits the north pole. Okay, so if I make this this difference very small, so that the band structure is only significantly affected near the Dirac points, then basically the d vector is going to spend most of its time living in the xy plane. Okay, except near k and k prime, it's going to go up to the north pole. Okay, so if I think of this d vector as a function of the two-dimensional momentum, then it's clear that it doesn't wrap around the sphere. Okay, it's sort of draped over the top of the sphere, but it doesn't have any wrapping. So the wrapping number of this is going to be 0. The Chern number is 0. So this is a trivial insulator, which in fact it has to be, because you could turn up this gap really big, and then this thing just turns into a atomic insulator, the most trivial insulator you could imagine. Okay, all right. But you could do something else. Okay, and so this is the insight that Duncan Haldane had, many years ago, which is that there's another way you can open a gap at the Dirac points, which is not by putting, this is like putting on a periodic electric potential. You can put on a periodic magnetic field. Okay, and so now, so what Duncan imagined doing was applying a magnetic field which is not uniform. It's 0 on the average. Okay, and if it's 0 on the average, that means that the net magnetic flux in any unit cell, in any hexagon, is equal to 0. Okay, and that means that you still have Bloch's theorem. So you can still think of you still have a band structure where I can think of the lattice translations still commute with each other. So I can still think of the Hamiltonian as a function of crystal momentum kx and ky. Okay, but since I have this periodic magnetic field, I have broken time reversal symmetry, the symmetry under reversal of time. That's what the magnetic field does. And so breaking this symmetry also allows the it allows the so breaking this symmetry allows the D vector to come out of the plane. Okay, but now the k and minus k, if they're related by time reversal symmetry, it has to visit the north pole at k and the south pole at minus k. Okay, and if it does that, then again, you're spending most of your time living on the equator, but near the k point, it goes to the north pole, and the minus k point, it goes to the south pole. So this, you can see, wraps around the sphere. Okay, and so this has a winding number of 1, so the Chern number is equal to 1. Okay, and so in doing so, what Haldane did is realize that you could have a quantum Hall state without a uniform perpendicular magnetic field. Okay, now there's a way you can think about this, which is which makes this seem almost completely trivial. So if you like thinking about the uniform magnetic field Landau level, okay, what you can imagine doing is taking that problem and then drilling a bunch of little holes in your quantum Hall state. Okay, and drill one hole per flux quantum that you have that's making your Landau level. Okay, and then what you do is through those little holes you thread a quantum of magnetic flux that's opposing the uniform magnetic field you have. Now, threading a quantum of flux through a little hole has no effect at all on the spectrum, right? Because you can just gauge it away. Okay, but what this opposing magnetic field does is it cancels out the uniform magnetic field on the average. Okay, and that morally that's exactly the same as what this is. Okay, so you do not need to have a uniform magnetic field in order to achieve this integer quantum Hall state. Okay.
What's an n equals 2 state?
What's an n equals 2 state?
Sure.
2 copies of the n equals 1 state. 2 layers of graphene. Yeah. So you want to have an n equals 2 state with just the single layer of graphene. Okay.
Number 2.
Yeah. So you could do that, though it's not going to be. So you'd have to write down you'd have to do more drastic modification of the band structure in order to do that. You see, the virtue here is I'm able to get n equals 1 with just a very small perturbation to the graphene. I'd need to do something more drastic in order to get to n equals 2. I could write down a model for you that would do that. I could. It wouldn't look very much like graphene anymore. Yeah, no, so it's yeah, one could do it. Yeah.
So when you say that your D vector is wrapping around the sphere, do you mean that it is gone through all the points of the sphere in the sense it is spanned the entire sphere?
Yes, every point. Yeah.
Every point is gone through.
Yeah, absolutely. Yeah. Yeah. Parity is broken by having these 2 atoms be different. So it's like so what that means is that there's a energy which is different on the A sublattice than there is on the B sublattice. So that means I put in a term proportional to sigma z. Excuse me? Well, no. I could say, so what I could do, if I want to physically do that, I'd make the 2 atoms different on the A and B sublattices, different atoms. So there's another compound which is like that, which is called boron nitride, where there's a boron atom on the A sublattice and a nitrogen atom on the B sublattice. Okay? And so that's like this. Okay? Now, of course, in boron nitride, the mass is really big. Okay? So, but yeah, has the same symmetry. What for? You have to apply now. Of course, you have to apply a magnetic field, but you're not applying a uniform magnetic field, and you have to apply periodic magnetic field. And so 25 years ago, when Duncan did this, he writes at the end of the paper, it's unlikely we'll ever be able to do this. Okay, but now, of course, we've figured out how to do it. So, all right. Yeah.
Break both P and T, is there some competition between the two?
Yes, that's right. Absolutely. Yeah. Yeah. So there'd be a exactly. Yeah. Okay. All right. Now, so the question is whether this is all there is to it. Okay. Is there anything else that could happen? And so this is where. Actually, so let me just say one more thing, which is the interesting thing is what happens at the interface between these two. Okay, and at the interface between these, you get edge states, and we can understand these edge states in just the same way that we understood the domain wall state in the Suchere-Verheugen model. Okay, so if we have a boundary between n equals 1 and n equals 0, I can think of that as a boundary between this and this, where I just change the sign of the mass term at one of the k points. Okay, and so at one of the k points, on this side I have the masses are opposite each other, and on this side the masses are equal to each other. And so you can solve this in exactly the same way that we did the Suchere-Verheugen model, where now what I can do is for every, I can look at the eigenstates of ky, the eigenstates which are plane waves going in the y direction, and for each value of ky, I just have a, one-dimensional domain wall problem. It has exactly the same solution, and so the zero mode state that you get then turns into this this chiral Dirac fermion mode that has a uniform velocity. And I guess I should have written down here. So this zero mode that you get is going to be a eigenstate of sigma y, basically. Okay, so when you solve for the zero mode as a function of x, that zero mode is an eigenstate of sigma y, and so therefore you can see that its energy is just going to be linear in ky. Okay, so these edge states are sort of wonderful and magical because they only go in one direction. Okay, and so they're sort of like one-way streets. And so this is very interesting because if you put in an electron here, it basically has no choice but to go forward, so that with 100% certainty it's going to come out the other end. So it has perfect transmission, and that perfect transmission allows you to measure the quantized transport in the quantum Hall state, to incredible 1 part in a billion accuracy. Okay. Okay, so this is important. Now an important thing is that having a mode like this is something that can't happen in a purely one-dimensional system. Okay, and so there's this theorem called the fermion doubling theorem, which was once explained to me as simply the fact that what goes up must come down. So if you had a one-dimensional band structure so then it's going to be defined on a circle. So if you have a band that comes up, it has to connect back to itself, so it has to come back down. Okay, so in a purely one-dimensional system, you have to the chiral fermions have to come in pairs. And so what the quantum Hall effect accomplishes is spatially separating the right movers and the left movers. It puts the right movers on the top edge, and then on the other edge are the left movers. Okay, so it spatially separates them. Okay. All right. All right. So I think maybe I'll skip this. So what I want to do now is I want to ask whether there's anything else that could happen in graphene. Okay, and so this gives us something interesting conceptually. And so let me sort of summarize the way we thought about this, which is that and now I'm going to remember that the electrons actually come in two flavors: spin up and spin down. Okay, and so the important thing is we had these Dirac points where there are two valleys at k and minus k, and then I have this sublattice sigma index, and then S is the spin. So when I had a trivial insulator, that gave me a mass term which was sort of the same at kx and ky, and it's also the same for all the spins, and this mass term breaks inversion symmetry. Okay. Likewise, I could do the Haldane mass term, which gives me a mass term which again is independent of the spin, but has opposite signs at the k and k prime point. Okay. And so the problem is both of these break a symmetry that graphene has, and so real graphene shouldn't be in either of these two states. Okay. But it turns out that if you have a mass term which looks like this, so it's just like the Haldane mass term, but with opposite signs for the up and down spins, then this respects all of the spin symmetries that graphene has. Okay? So, because the problem with this one is that under time reversal symmetry, it was odd. Okay, like it's like a magnetic field. It's odd under time reversal, but you see the thing is that under time reversal, the up spin goes to the down spin, and so that putting the spin in here fixes that. Okay, so in principle, this involves an interaction between the sort of orbital degrees of freedom of the electron and the spin degrees of freedom, and so it requires a spin-orbit interaction. But this interaction should, in principle, open up an energy gap. Okay, so when I first thought about this, I thought, I've discovered that graphene is actually an insulator. Okay, now the problem with this argument is this is an argument based on symmetry, and symmetry arguments are wonderful because you can know that they're right. But what they don't tell you is they don't tell you how big an effect is. Okay, and the problem is that this spin orbit potential in graphene is puny. But nonetheless, it's something interesting to think about, because what it tells us is that we have an energy gap, but it's really just two copies of the Haldane model. Okay, one for the up spins and one for the down spins. Okay, because this mass term is just SZ. It's just the up spins have this with a plus sign, the down spins have this with a minus sign. Okay, and so that means that the up and down spins independently are in integer quantum Hall states. Okay, and so we have an energy gap, but we have to have chiral edge states. Okay, and these chiral edge states are something interesting because the up spins are going one direction and the down spins are going the other direction. Okay, and so we now call these edge states where the direction of motion is correlated with the spin. We call them helical edge states. Okay, and so these are also something which is very special. Now they're not quite as special as the quantum Hall state, the chiral edge states. Okay, remember the chiral edge states, you had no choice but to go forward. So these edge states, you can go backwards. Okay, but there's a sense in which they are protected, which I'm going to describe, which these are protected by time reversal symmetry. Okay, and really there's a sense in which these edge states form half of an ordinary one-dimensional electron system. So an ordinary one-dimensional electron system with spin, it has up and down spins going to the left and up and down spins going to the right. This one is only half of that. Okay, so let me say a few words about time reversal symmetry, because this is really something which is important. I want to make sure everybody is on board with. So time reversal symmetry is a kind of not your usual kind of symmetry that you learn about in beginning quantum mechanics. Okay, so usually you think of symmetry as a unitary operator. This isn't. So time reversal symmetry is an operator which, in addition to doing some unitary operation, it takes the complex conjugate of the wave function. Okay, and so it's an anti-unitary operator. Okay, so it does two things. It takes the complex conjugate of the wave function. It also flips the spins. Okay, because the spins are sort of like tops; they change sign under time reversal. Okay, and it has a very important property, which is this minus sign here. Okay, so which means that if you do time reversal twice, it squares to -1. Now this -1 here it's really the same minus sign that you get if you take a spin a half and you rotate it by 360 degrees. Okay, this minus sign is the same minus sign. Okay, so but this minus sign has a very important consequence, which when I first learned it, I thought it was completely trivial, but now I realize it's not as trivial as I thought. And the consequence is Kramer's theorem, which says that if you have a spin a half system, and you have time reversal symmetry, then every eigenstate is at least twofold degenerate. Okay, and so the reason I thought it was trivial when I first learned it is because because when I first learned quantum mechanics, I never thought about the spin-orbit interaction. So that means if you have a state, you can put an up spin in it, or you can put a down spin in it, and those two states are degenerate. Okay, so Kramer's theorem just says you can either put an up spin or down spin. Where Kramer's theorem becomes non-trivial, though, is when you have an interaction between the spin and orbital degrees of freedom. So I can't think about the spin independently of the orbital state that I'm putting it in. But it's still true. And so let me just show you how we know it is still true. So imagine that you have a state, okay, and I can then the time reversal of it, I have an eigenstate of the Hamiltonian. I have the time reverse of that eigenstate, is some state. And so if I do time reversal twice, then the point is it takes the complex conjugate, and so that gives me c squared, which cannot be equal to -1. Okay, and so what this means is that the time reverse of this state cannot be equal to itself. Okay, so I cannot have. So if I had a singly degenerate state that was an eigenstate, then it would have to be its own time reverse. Okay, so that's impossible. So when theta squared is equal to -1. Okay, and so the consequence of this is that for these edge states so notice that that these edge states they cross each other. Okay, and so your first thought, when I first learned quantum mechanics, one of the things I learned is that if you have a degeneracies never happen by accident. Okay, if you have a degeneracy, then if I just do a small perturbation, then that degeneracy should be lifted, and then there should be a little gap that opens up here, and then there's nothing. Then there's nothing left. Okay, but what time reversal theorem tells us is that the two states that are crossing actually form a Kramer's pair. Okay, so they're crossing at this corner at this edge of the Brillouin zone where k and minus k are the same point. So these two crossing states are in fact a Kramer's pair. Okay, and so what that means is that as long as you keep time reversal symmetry, there's nothing you can do to open up this energy gap. Okay, so the crossing is protected even if the conservation of spin is violated. Okay, so even if spin itself is not a good quantum number, if you have a spin-orbit interaction, then this crossing is still protected. Yes?
So time symmetry ensures that you have these degenerate states at the symmetry-protected points.
Yes.
But I can consider other models where I take out time symmetry, but I put in another symmetry that gives me degenerate states at the symmetry-protected points. My question is that a general statement that if I have just a symmetry that gives me this type of degeneracy at a symmetry-protected point, I can have these sorts of edge states?
Well, I mean,
like, is there something special about time reversal, or can it be another symmetry?
Sure, you can have other symmetries that protect things. Yeah, that's right. And that is true. So the thing that's special about time reversal symmetry is that it's not a spatial symmetry. So that you can have disorder and still have time reversal symmetry. Okay? And so that makes it more robust in terms of describing physical systems. So if you have other spatial symmetry, like a reflection symmetry, so you can have degeneracies which are protected by a reflection symmetry. And this is actually something that people are currently talking about a lot with topological crystalline insulators. Okay, they have edge states that are protected by that rely on a reflection symmetry. But if you make them dirty, then they are less. Then disorder violates the reflection symmetry. You're never going to have reflection symmetric disorder. Okay, so at least if you did, that would be very artificial. So that's the sense in which time reversal is more robust. Yeah. Yes. Well, so I use the fact that the spin is an odd integer 1/2. So you know the minus sign that you get when you rotate a spin by a half is if it's a half integer you get a minus sign. If it's an integer spin you get a plus sign. Okay. Yeah. Yeah.
So you think you see that minus sign from time reversal is the same as the minus sign?
Yeah. So if you square it, if you square this, then I think you end up with a 2 pi rotation about sy. Yeah. So so if I write this down, then I can write the time reversal operator as complex conjugation and then some rotation of the spin, and yeah.
What's a Kramer's pair? Use the word Kramer's
A Kramer's pair is the two degenerate states.
Individually, or is some linear combination of them?
No, it's a pair of states, right? Which are the time reverses of each other.
Okay, for the entire band structure.
No. It's just these two states. It's just for one. It's only for the. You see. In the band structure, time reversal takes k to minus k. So it only makes sense to talk about Kramer's theorem at the values where k and minus k are the same point. You see, because the Kramer's. So if I have a non-zero value of k. Oh, great, thank you. If I have a non-zero value of, if I have a non-zero value of k, then its Kramer's partner is at minus k. Okay, so in general, at a non-zero value of k, the states don't have to be degenerate because you have the degenerate state is at minus k. But if you're at k equals 0, then 0 is equal to minus 0. So that means the Kramer's partner has to be at the same momentum. Okay, and so that means the two states at that momentum have to be degenerate, and they form a Kramer's pair. So I guess so you have a Kramer's pair at non-zero k, but then it's going to be k and minus k. Now there's another point at the edge of the Brillouin zone, k equals pi, which is also equal to minus pi. Okay, and so that's important. Great, thank you. Okay, so right, and so this fact. Actually makes these edge states sort of more robust than you might think because it prevents the backscattering of electrons in these edge states, at least by elastic backscattering. Okay, and another feature that this gives. So in a one-dimensional system, if you make it a little bit disordered, then it will be unstable to Anderson localization. Okay, and so one-dimensional electron systems are unstable. This is sort of a one-dimensional system on the edge here, and it is able to evade Anderson localization because of this absence of elastic backscattering. And even for strong disorder. I think I will be able to convince you that this cannot be localized even if you have strong disorder. Okay. Pardon? Sure. There can be further accidental degeneracies. Or if you have other symmetries, there could be other symmetries which make the degeneracy higher. Yeah. I'm sorry, could you speak a little bit louder? I couldn't hear.
So less familiar with the Anderson localization. Can you explain the last statement?
Well, okay, yeah. So let me wait until the next view graph to try to explain. So in general, if you have a disordered system, then you can have localized. Then your states can be localized. You can imagine, if you have a really big disorder, then there's going to be like the lowest energy is you're going to have a localized state there. And the theorem is that in one dimension, no matter how weak the disorder in an ordinary one-dimensional system, no matter how weak the disorder is, you flow to the Anderson insulator. Okay, and so this system is a little bit different. And I think in the next view graph, I might be able to give you an argument that will convince you that this can't be localized. So I'll see if I can do that. So this poses the question, so there's something very special about this quantum spin Hall insulator that we sort of stumbled on thinking about graphene. Okay? And so what is it about the bulk that tells it that it has to have these special edge states which are protected by time reversal symmetry? And so there must be some topological structure. And so in fact there are two and only two topological classes of time reversal invariant insulators. And just so I have an idea, so I'm going till 11, is it? Okay, good. Okay, so let me convince you that there are two and only two classes. Okay, and again, the way I'm going to do this is by thinking about the boundary, about the edge of this two-dimensional system. Okay, and so again, I have a two-dimensional Hamiltonian with time reversal symmetry, which imposes this constraint. And so I want to argue that there's a Z2 topological invariant that distinguishes two different kinds. And so if I think about the edge states, so let me go back to thinking about these edge states, and so in general, so what I'm going to do is I'm going to plot the energy bands as a function of momentum along, say, a strip. Okay, so and I'm only plotting half going from k equals 0 to k equals pi. The other half going from k equals 0 to minus pi is, because of time reversal symmetry, is just a mirror image of this. Okay? So now, so at k equals 0, I have the valence band and the conduction band, and it's always possible, depending on what the details of the potential at the boundary is, that there could be states which are inside the energy gap but are localized at the edge. Okay, so that's always possible. But the thing that we know is that if we have time reversal symmetry, then they have to be Kramer's degenerate. Okay, there have to be two states. Now, if I move away from k equals 0 and I have a spin-orbit interaction, then in general this Kramer's degeneracy will be split because, again, this guy's partner is at minus k. Okay, so these states have to be Kramer's degenerate. Now, at k equals pi, again, since pi and minus pi are the same momentum, these also have to be Kramer's degenerate. Okay, so now you can understand why it is that there are two and only two classes. It's because there are two and only two ways that the Kramer's pair here can connect with the Kramer's pair here. Okay, either they can connect pairwise like this, and if they connect like this, then the way I've drawn it here, I have some edge states. Okay, there are states at the Fermi energy on the edge, but those edge states don't have to be there. They might be there, but they don't have to, because I can imagine pulling these down smoothly and just getting rid of them completely. Okay? So you might have edge states, but you might not. Another way you can say it is that the number of intersections of the Fermi energy of the bands in between k equals 0 and pi has to be even. Okay? So it could be any even number. That even number might be 0, so you don't have to have the states. Now, the other way you can do it is they could could sort of switch partners. The Kramer's pairs could switch partners going from 0 to pi, and if they do that, then there's no way you can get rid of them. Okay, you can move these up and down all you want. There always has to be an odd number of crossings in between 0 and pi. Okay, and so so these ones you can see that you can't get rid of. Okay, so now let me try to answer the question about Anderson localization. And so I'm going to play the same game that I played with Laughlin's argument in the quantum Hall effect. What I'm going to imagine is that I have a big system, okay, which is disordered, but I'm going to put it on periodic boundary conditions. Okay? And then what I want to do is I'm going to consider my entire system to be one single unit cell. Okay? And so, so then it has a band structure, okay, and so then I can have a magnetic flux that changes the boundary condition for how the wave functions here match up with the wave functions on the other side. Okay, so I can twist the boundary conditions, and that is like changing the value of K in this single unit cell. Okay, now if it is a topological insulator, then the spectrum of the edge has, now there are going to be lots and lots of states because it's very long, but if I follow them, then the Kramer's partners, since it's finite, then the spectrum at the edge is going to be discrete, and it's going to have Kramer's partners which switch partners as a function of K. Okay? Now, if you were Anderson localized, then your states would be exponentially localized, and there's no way they could know what the boundary condition is. Okay? So by definition, localized states are insensitive to the boundary condition. So if you had localized states, there's no way they could have this zigzag partner. Okay? And so that guarantees that every state here is extended and goes all the way around, and every state knows about the twisted periodic boundary conditions that you put on. Okay, and so that guarantees that that these states cannot be Anderson localized. Yes.
So, if they switch partners, that sort of guarantees that you need two edges, sort of a strip. What I'm imagining.
Well, you do need two edges, but why are you saying that that you need two edges of this? I mean, this picture here is all characterizing just a single edge. There's going to be another set of these pictures which are localized on the other edge.
Right, that's what I'm asking about. Is system with just one edge physical?
No. So I can't, with time reversal symmetry, I cannot have this picture in a purely one-dimensional system. Yeah, it's just like I can't have a single chiral edge state. Okay, so I cannot have the helical edge state in a purely one-dimensional system. Yeah.
Going back one slide, just to look at a simpler picture. Can you go back one slide?
Sure.
So at this direct point, if I define projection operators, let's say for the green line, so that I project onto that eigenstate, and I vary as I go along the green line, and I come back because I have this rho 1 torus.
You mean I'm going all the way around?
I'm gonna end up on the red line, right?
Ah, no. You see, that's the reason. That's the origin of the doubling theorem. You see, what has to happen is as you go along, you have to intersect the bulk states. You see, this state is not coming and matching up onto this one. So in fact, what will happen, so if I do it in a finite strip, what you will find, in fact, is that if you follow this discrete state around, what will happen is it will come back on the other, it will mix with these states which are extended across the entire width of the strip, and then this state will come out on the other edge. Okay? And that's the same thing that happens, maybe it's more obvious that that's what happens if you have the, let's say I don't have the, yeah, say if I have this picture, okay, so this picture is on one edge, okay, so you could ask, well, what happens to this if I follow it up? Well, what happens is it comes out, on the other edge there's a line that's coming down like this, okay, so that's what happens to it. Okay. Good.
Sorry, just a quick if you have translation symmetry breaking disorder,
Yes.
then how do I visualize that K-space plot? In principle, that whole thing.
Well, no, that's the reason why I gave this argument, which was I want to think of the entire system, which is disordered now, as being my unit cell. So then the momentum, the K that I'm using here, is really the phase twist of my boundary condition. Okay, and so that I'm allowed to do even when I don't have, so in a sense I have a translation symmetry, which is that, I have the periodic boundary condition, so I can, it's like I'm making, you can think of it, I'm taking my system and I'm making many copies of it, periodically extended, and then thinking of that as a band structure, right, with K. That, you could think of that's what I'm doing. But I don't think I'm relying on the translation symmetry of the lattice translation symmetry in order to do this. Okay. All right. Let's see. Where are we? Okay. So let me try to. So we have. There's this. So this tells us that there should be some. Topological invariant that has two values, 0 and 1, okay, which tells us whether the edge looks like this or whether it looks like this, okay? And so in the Laughlin, in the quantum Hall effect, we had this very nice physical picture of what the Chern number meant, okay? In terms of the Laughlin argument, if we thread a flux, then it tells us how much charge is pumped. Okay? And so let me try to give you a similar understanding of the Z2 invariant in that case. Okay? Because the sort of mathematical description of the Z2 topological invariant is a little bit harder than the Chern number. Okay? And so let me try to give you some physical picture. So let me remind you that if we do the integer quantum Hall effect, we thread a flux down the cylinder, and then we pump an integer number of electrons, and that's the Chern number. Okay? So now let's imagine that I wrap this quantum spin Hall effect on the cylinder. And I can think of it that, it's like I have two copies of the quantum Hall effect, +1 for the upspins and -1 for the downspins. Okay? And I want to think about a similar sort of flux threading Gedanken experiment. And but now what I want to do, now obviously if I thread a flux, then a whole flux quantum, then the Chern number is equal to 0, so I come back, no charge is pumped. Okay? But what I want to do is I want to think about what happens when the flux that I thread is 1/2 of a flux quantum. So I thread a flux h over 2e. Okay? Now, the thing that is special about h over 2e is that, you can always gauge away an integer number of flux quanta, right? So 0 is the same as h over e, which says that h over 2e is the same as minus h over 2e. Okay? And so what that means is that when you have the flux of h over 2e, you basically have time reversal symmetry. Okay? So there are 2 points where you have time reversal symmetry. You have time reversal symmetry at 0 flux, and you have time reversal symmetry at flux h over 2e. It's sort of like, in the Brillouin zone, you have time reversal symmetry at k equals 0 and at k equals pi. Okay? It's the same sort of thing. Okay? So let's think about what happens if I thread a flux of h over 2e. Now, of course, I break time reversal symmetry in between, but at the beginning and at the end, I have time reversal symmetry, which means I have Kramer's theorem. Okay? And now I want to think of Kramer's theorem. So what happens is that when I thread half a flux quantum, then what I'm going to do is I'm going to transfer half of an upspin to the right, and I'm going to transfer half of a downspin to the left. Okay? So at the end of the day, I have changed the local spin at the end by a spin a half. Okay? And so what this means is I have gone from locally having a ground state where all of the states are paired, so there's no Kramer's degeneracy in my ground state, to a state where I have a single unpaired spin a half. So I have a Kramer's degeneracy. So now I'm talking about the sort of many-body states. I go from locally having no Kramer's degeneracy to locally having a Kramer's degeneracy. Okay, and so this is so if I had a trivial insulator, then it would have to be insensitive to the magnetic flux, and so this couldn't happen. Okay, and so this is what happens if I have a topological insulator. Okay, all right. Do I want to do this? Does anybody want to know what the formula for the Z2 invariant is? We can skip this and talk about. I think maybe I will. This is a little bit technical, so I think maybe I will skip this and go to. So you can calculate this Z2 invariant. Given a band structure, you can calculate it. Okay, and it's not that easy to do, but there are different ways you can do it. Some of them are more easy to implement on a computer than others. This one is not so easy to implement on a computer. So what it is easier to do is to figure out the Z2 invariant when you have some extra symmetry. Okay. So for instance, if you have the conservation of SZ, like I did in the model, which was just 2 copies of the Haldane model, the Hamiltonian only involved SZ, so SZ commuted with the Hamiltonian, which means I really could think of it as 2 independent quantum Hall states for the up and down spin. Then the up and down spins each have their own Chern number. Okay, which of course time reversal symmetry says they have to be opposite to each other, but the Z2 invariant is just the parity of those Chern numbers, whether they're even or odd. Okay, and so this of course survives even then if I turn on a perturbation which violates the conservation of spin. So there's another symmetry which actually turned out to be quite useful that one can think about. Which is to think about a system that has inversion symmetry. And then it turns out that one can figure out the Z2 invariant just by thinking about the parity of all of the occupied block states at the different parity invariant points. So in a 2-dimensional band structure, there are 4 of these points where k and minus k are the same point. Okay, I can have 0, 0, pi, pi, 0, pi, and pi 0. Okay, and at all of those points, the eigenstates, if you have inversion symmetry, are going to be parity eigenstates. So they're either even or odd under parity. Okay, and so if you take all of those eigenvalues at all of the parity invariant points and you multiply them together, then you get something which is either plus or minus 1. And if it's minus 1, then it's guaranteed that you have a topological insulator, if you have an insulator. Okay, so this actually is a sort of, if you have inversion symmetry, this is a quick way of determining whether you have a topological insulator or not. And actually, historically, that's the way we sort of figured out the first example of a topological insulator, which was this alloy of bismuth and antimony that Zahid told you about yesterday. Okay. Let's see. What to do? I think what I'm going to do is I'm going to skip. I think Amir Yacobi is probably going to talk about the mercury telluride experiments, which were the sort of first experiments that demonstrated the 2-dimensional quantum spin Hall effect. So I think I'm going to skip through this, and so I want to get to the 3-dimensional topological insulator. So what we introduced was so now we understand that in 2 dimensions there are 2 classes of insulators. Okay, so there's the topological insulator and the trivial insulator. And so the natural question that you can ask is, what about three-dimensional crystals? Could there be topological classes of those? Okay, and so in fact the answer is yes. And again, the sort of a simple way that you can think about it is to think about what happens at the boundary. Okay, so now the boundary of a three-dimensional system is a two-dimensional plane, and so I can ask myself, what sort of kind of surface states could I have now as a function of momentum in this two-dimensional Brillouin zone? Okay, so again, the story is the same as in the edge state case, where there are certain points where k and minus k are the same point, and at those points, surface states which are localized at the surface inside the energy gap, if they exist, they have to be Kramer's pairs. Okay. So for a two-dimensional surface, there are 4 of these special points, and at each of these special points, I have to have this Kramer's degeneracy. If I move away from these points, then again, in general, a spin-orbital interaction will lift the degeneracy. So each of these Kramer's degenerate points, each of these points is really going to be a two-dimensional Dirac point. Okay, where this degeneracy is really protected by time reversal symmetry. And so you have lots of Dirac points on the surface, but the interesting question is how they connect up with each other, okay? Because either they can connect up with each other, if they all connect up with each other like this, then you just have a trivial insulator, because I could get rid of the surface states. I could just pull them all down into the valence band, okay? But if they connect like this on any pair of these, then I have something that I can't get rid of. Okay, so maybe you can sort of see that since now I have 4 of these different pairs, that it's actually a little bit more complicated. There are more ways. I could have some of them. Some of the pairs could look like this, and some of the pairs could look like this. And so maybe there's a little bit richer structure. So it turns out, in fact, there are 4 Z2 topological invariants that summarize the topological structure of a three-dimensional crystal and tell you whether the picture looks like this or this on any surface. Okay, and so 3 of these invariants, I think, as Zahid mentioned to you yesterday, are really just characterizing what we call a weak topological insulator, where I can think of that as just stacked, layering two-dimensional topological insulators on top of each other, just forming a stack. You see, because if I do that, then what you know is if I just stack them and they're not talking to each other at all, then on the side surfaces I'm going to have the helical edge states going along. Okay, and so if I think of that of the band structure of that, then there will be sort of a Fermi surface that looks like this, and then if I couple them together a little bit, then the Fermi surface will sort of bow out a little bit. Okay, and so this is a weak topological insulator. The important thing here is that this Fermi surface on the surface, it encloses 2 of these time reversal invariant Dirac points. Okay, the more interesting situation is the situation where what we call a strong topological insulator, where the Fermi surface just encloses on the surface just encloses a single one of these Dirac points. Okay, and so this case is the case which is sort of more robust, and so again, in this case, these states are impossible to localize even with strong disorder. Okay, so they have the same sort of robustness as the helical edge states of the quantum spin Hall insulator. Yes. Yes. So the top surface wouldn't have anything.
So then, is this structure dependent on which edge and what symmetry?
For the weak topological insulator, yes, it is. For the strong topological insulator, no matter what edge you choose, There will always be an odd number of Dirac points enclosed by your Fermi surface. No matter what, yeah. Of course, there could be 3 instead of 1, but there can't be 0. Now, on the weak topological insulator, the Fermi surface encloses an even number of these Dirac points. Okay, and on some surfaces, that number could be 0. So, for instance, on the top surface of a stack of two-dimensional topological insulators, you don't have any surface states.
It seems to me like you're characterizing information about the three-dimensional topological insulator just in terms of one of these surfaces. Is that?
No. I mean, so these topological invariants are defined independent of the surface. So they characterize the bulk. And so what I'm saying is that the different possibilities that the surface can have are these. And so the question is, what is the structure in the bulk that determines whether which picture you have on the surface? Okay, and so So at this point, I haven't explained to you, how we determine these bulk topological invariants.
And the possible surface Brillouin zones that we can write down are a subset of the Brillouin zones that we would write down for a two-dimensional system, correct?
Well, the Brillouin zone is the same, but if the structure looks like this, then this could not be a structure in a purely two-dimensional system. Right, because this thing, in a two-dimensional system, you don't have the conduction and valence band. Yeah. So this could not exist in a purely two-dimensional system. Yeah.
So when you look at the invariant on the edge, but we're looking at the band dispersion, you can kind of, as you said, in like specific cases, just kind of pretty simply pick it out. For these topological invariants in the bulk, are you doing something like integrating the wave function over the three-dimensional Brillouin zone?
So let's see. Okay. So let me just tell you a little bit about how you can think about these three-dimensional invariants. Okay. Do I need to stop? Maybe
about wrapping it up for an hour.
Okay, so let me just say one word about how we determine these three-dimensional. You see, so one way, there are different ways you can do it. One way you can do it is by thinking of the so in a three-dimensional system, in the three-dimensional Brillouin zone, there are two-dimensional planes which are time reversal invariant. Okay, like the plane kz equals 0 is a time reversal invariant plane. So that plane itself has a two-dimensional Z2 invariant. I can think of that as being like a two-dimensional system. The plane kz equals pi also has a Z2 invariant. So each of these planes has its own Z2 invariant, and by knowing those, you can figure out what all of the 4 Z2 invariants is. Okay, and so in particular, the strong Z2 invariant is what happens if you have the plane at k equals 0 is not equal to the plane at k equals pi. Okay, and then if that's the case, you can show that that is true for all 3 of these pairs. And so that's what the strong Z2 invariant is. Whereas the weak Z2, if you have a weak topological invariant, then you have something where this one and this one are the same. And that could happen if you just have a stacked system where it's independent of kz. Okay. All right. So yeah. So yeah. So I'm finished with what I'm going to say. So then we can have some more questions.
When you say topological insulator, it's still fairly robust like perturbations, right? You can actually move the directions to each other fully. Is that cool?
Which Dirac? You're talking about these Dirac cones?
Yeah.
No, they can't move because they are guaranteed by time reversal symmetry.
Oh.
They're stuck where they live.
How can you bring weak topological insulators?
Oh, okay, very good question. So in order to break a weak topological insulator, what you need is a perturbation that couples this Dirac point to this one. So you need to lower the translation symmetry. So if I was to put on a periodic, if I was to double the unit cell and put on a periodic potential which lowers it, so I have to go by 2, then I would fold this Dirac point back onto this one. And then I could have a perturbation which couples them together and opens a gap. Yeah.
Can you do it any, like, I know with graphene you can do it deploying lattice or something to buckle it in some way.
Right, but so in graphene, the Dirac points are not protected by, it's time revert. They can move if you, yeah. Okay. All right. Any other questions?
Okay.
Okay, good.
Thank the speaker.